Hi, I'm Anirudh, and welcome to Baseline. I really appreciate you taking the time to learn more about my project. So we'll just get into it. Baseline is a scientifically validated music intelligence platform that uses continuous emotion classification to deliver personalized music recommendations across 1.2 million tracks for stress relief, mood management, and music discovery. Not only does Baseline provide recommendations for playlists, but it also integrates a Spotify player, which is able to play the songs if you have Spotify Premium. In the stress relief feature, you are able to choose between 4 stress types and receive 20 recommended songs to help with your unique selection. If you are having trouble choosing, you can choose instant stress relief to get 10 tracks to help with any kind of stress. Mood management is a feature that you can use to process your feelings, feel a gentle uplift, or boost your energy levels. Music is very personal. A song that may relieve stress in you may do the opposite for someone else. You can teach Baseline your music taste profile by rating random songs in the Discovery Lab in order to get the right recommendations for your personality. The first thing I want to discuss is the machine learning and data pipeline. Data collection was done by fetching 1.2 million songs and their audio features from a Kaggle dataset. I used the database for emotional analysis of music called the DEEM dataset to train random forest models that predicted the valence and arousal of all the songs based on audio features taken from the Kaggle dataset. After the models were trained, they were applied to the full dataset. This split the dataset into 2 groups, 800,000 calming tracks and 400,000 stressed tracks. Using the DEEM dataset and Russell's circumplex, I created 9 categories with different percentile thresholds for arousal and valence. I then inserted tracks into the PostgreSDB, and the songs were annotated with category thresholds using where clauses. Finally, I validated the emotion predictions using a train test split, ensuring the model accurately predicted valence and arousal for unseen tracks. Track assignments were verified by checking that category distributions matched expected percentile ranges and that each track fell within its assigned category threshold. The first core issue I ran into in the emotional classification of music was that I was putting all of these songs into discrete binary categories, but that's not actually how it works. How a song makes you feel depends upon its particular arousal and valence values, and where those values make a song land on Russell's circumplex seen here on the screen. This is why I used the continuous valence arousal scores from the DEEM dataset as training labels for a random forest model that predicted arousal and valence values for each of the songs. These models were used to calibrate Spotify's features to better match human emotional perception. All of this classification is used to decide whether a song should fall in the stressed zone or the relaxed zone. After the valence and arousal values are normalized on a 0 to 1 scale, this is what the valence arousal plot ends up looking like. The songs are mapped into 9 separate categories, which are further used to identify which contexts these songs would best be used in. A slightly easier way to understand valence and arousal is that valence is about how much you vibe with a song, and arousal is about how much energy the song brings to you. Songs that were found in the relaxed zone were further distributed into 9 wellness categories, and these categories define where these songs are played in the various services. These are the machine learning pipeline's validation metrics. Since the tracks are distributed based on a percentile system, it avoids hard coding certain tracks as a certain category, and this allows me to change the thresholds of those categories in the future without having to mess with the actual database. Now, moving on to the backend architecture. I designed a 3-layer architecture separating API routes, business logic, and data persistence. This enables clean code organization, easy testing, and performance optimization with strategic caching. Caching is done with Redis to increase speed, as database queries are too slow for instant stress relief responses. On app startup, 20 Ultracom tracks are loaded from PostgreSDB into cache. If the cache hits, songs load within 50 milliseconds. If the cache misses, tracks are queried from the database, and this takes up to 500 milliseconds. Pydantic is used for automatic data validation, and this helps automate error handling. This is a general distribution of the endpoints created for Baseline. Now let's talk about Frontend Architecture. Layer 1 is used for user navigation, state management, API orchestration, and lifecycle management. Layer 2 contains feature-specific and shared TypeScript components, interactive elements, and display logic. Layer 3 communicates with the backend, contains Spotify integration, and manages state persistence. The Spotify Web API requires OAuth 2.0 authentication with PKCE to play music. Users log in about one time. Spotify gives Baseline a token. Baseline uses this token to play music. After an hour, the token expires and login must be renewed. PKCE prevents code interception, it's safe for browser based apps, and works on all platforms and devices. I used React hooks for state management. State flows unidirectionally from parent to child. I created 4 isolated React states. They are player state, playback state, volume state, and auth state. Each of these states change at a different stage in the UX flow and trigger different functions and components within the page. An example for playback state is user clicks play, the SDK player state changed fires, the listener catches this event, and set is playing is set to true. Button then re-renders and the play button becomes the pause button. One thing to note is that the local storage persists state while OAuth authentication takes place so that there is seamless transition when it redirects back to the service. The last thing to discuss is system logic. As you can see here, there are different features used to classify relaxed songs into buckets that can help users relieve stress in work, relationship, health, or financial contexts. Energy, arousal, tempo, valence are different features that are used here. The stress context selector provides users with 20 songs that are picked from different wellness categories based on 12 discrete combinations of stress and intensity. Mood management has 3 internal features: process your feelings, gentle uplift, and energy boost. Each of these features provides 20 tracks. Process mode and uplift mode use relaxed tracks, and energized mode uses all the tracks across the database. The discovery service plays a random track after excluding tracks that have already been rated. Rated tracks get saved to the track rating table, and this helps inform the gamified rating system. If more than 5 tracks have been rated, the threshold of songs that are recommended to the user is tweaked plus or minus 15% to better suit their taste. 70% of tracks recommended are chosen based on taste profile, and 30% are random to prevent users from existing in a musical echo chamber. Based on rating metrics, users' taste profile is displayed on the page. Thank you for taking the time to watch this video on my project. Find the project in the link in the description.